In other lectures, we described in detail heating, cooling, humidification and dehumidification of air. In this lecture, we will summarize this and you will learn how to combine this knowledge to control the temperature and the humidity of air. Each process will be explained on a representative example. There are only 8 processes. Too cold outdoor air must be heated to a comfortable temperature. Let's take outdoor air at 5 degrees and 30% relative humidity. We can read on the diagram that its absolute humidity X1 is 1.8 gram water vapor per kilogram dry air and its enthalpy is 9 kJ per kilogram dry air. We know that heating takes place along the line of constant absolute humidity because the mass of water vapor in the air cannot just disappear. So if we want to heat to 22 degrees, the final point is at the intersection of the temperature 22 and the line of absolute humidity 1.8. And the process is indicated by the blue line. At point 2, the relative humidity is 10% and the enthalpy is 26 kJ per kilogram dry air. The energy needed to heat the air is the difference in enthalpies, which is 26 minus 10 is 16 kJ per kilogram dry air. When handling air, we are handling flow rates rather than masses. The air is flowing. If we want to heat an airflow rate of 3 kg per second from point 1 to point 2, the heat needed will be Q is mass flow rate times H2 minus H1, which is 3 times 17 equals 51 kJ per second, which is the same as a heating capacity of 51 kilowatt. What if we now also want to control the humidity and make sure the relative humidity is 30% after heating? We start again from point 1 at 5 degrees, 30% relative humidity and absolute humidity 1.8 gram per kilogram dry air. Point 2, 22 degrees and 30% humidity is here, with absolute humidity 5 gram per kilogram. So, to go from 1 to 2, we need to heat and to add water vapor to the air. The quantity of water vapor that must be added is 5 minus 1.8 is 3.2 gram water vapor per kilogram dry air. But how does the process look like? Can you go in straight line from 1 to 2? Well, for sure not. It would represent nothing real. Let's do it correctly. The air must first be heated from 5 to 22. We have learned that it goes like that and will cost 17 kJ per kilogram heat. Adiabatic humidification follows a process along the constant wet bulb temperature lines, which have quite the same slope as the enthalpy lines. It goes therefore like that. And we have to stop the humidification process when the air has the right humidity, which is 5 gram per kilogram. This process does not cost energy as the enthalpy remains constant. We now have the right humidity, but the temperature has decreased to 13 degrees, so we need to reheat the air to 22 degrees following this line. So, for the first heating process, we need 26 minus 9 is 17 kJ per kilogram. The adiabatic humidification costs no energy and the second heating process needs 34 minus 26 is 8 kJ per kilogram. So in total, 25 kJ heat is needed and the adiabatic humidifier must provide 3.2 gram water per kilogram dry air. If instead of having 1 kilogram of dry air, we have 3 kilograms per second flowing, it leads to a heating capacity of 75 watt and a mass flow rate of 34.6 kilograms per hour. An alternative way of processing the air would be to heat it first much more up to the intersection of the wet bulb line from point 2 and the absolute humidity of point 1, which is here, corresponding to a temperature of 29.5 degrees Celsius, and to humidify it then down to the point 2. The advantage is that only one heater is needed. Energy used is unchanged. Let's now answer exactly the same question, but using this time steam humidification with steam at 130 degrees Celsius. We still have our starting point below at 5 degrees, and we still want to get the second point, by which we need to add 3.2 gram water vapor per kilogram dry air. We know that we need to heat the air, but how far? We also remember that steam brings heat. So, let's first look at how much heat steam will bring. You remember that we have to calculate delta H over delta X with this equation. From the table in the previous lecture, you can find that the latent heat of evaporation of water at 130 degrees is 2174 kJ, by which delta H over delta X amounts 2714 kJ per kilogram steam. So we have to draw a line from 0 to 2714 like that, and draw a parallel line going through point 2 like that. We can now determine to which temperature the air needs to be heated, and that is at the intersection with the absolute humidity line. X1 is 1.8 gram, giving a temperature of 21.3 degrees. The process takes therefore place this way. So, for the heating process, we need 25 minus 9 is 16 kJ per kilogram, and for the steam humidifier, we need 34 minus 25 is 9 kJ per kilogram. So in total, here too, 25 kJ heat is needed, and the steam humidifier must provide 3.2 gram water vapor at 130 degrees per kilogram dry air. If instead of having 1 kilogram of dry air, we have 3 kilograms per second flowing, it leads to a heating capacity of 75 watt and a mass flow rate of 34.6 kg per hour. Note that the total energy needed is identical for adiabatic and steam humidification and depends only on the start and final states. However, this heat is divided differently depending on the chosen process. Be also aware that the energy needed to make the steam is included in these calculations. Too warm outdoor air must be cooled to a comfortable temperature. Let's take outdoor air at 35 degrees and 35% relative humidity. We can read on the diagram that its absolute humidity X1 is 12.5 gram per kilogram dry air and its enthalpy is 68 kJ per kilogram dry air. We know that cooling takes place along the line of constant absolute humidity because the mass of water vapor in the air cannot just disappear. So if we want to cool to 22, the final point is at the intersection of the temperature 22 and the line of absolute humidity 12.5, and the process is indicated by the blue line. At that point, the relative humidity is 78% and the enthalpy is 54 kJ per kilogram dry air. The needed cooling is the difference in enthalpies, which is 68 minus 55 is 13 kJ per kilogram dry air. That must be removed. If we want to cool an airflow rate of 3 kg per second from point 1 to point 2, the cooling capacity is mass flow rate times H2 minus H1, which is 3 times 13 equals 39 kilowatt. It may happen that we need to cool air much further than 22 degrees. We will see in another lecture when that is needed. It may happen, for example, that at high cooling loads, air at 14 degrees is needed. We start again from air at 35 degrees and 35% relative humidity and apply cooling as we have just been doing. We have now one problem, and that is the dew point. When arriving on the saturation line here, the dew point temperature is 17.5 degrees and not 14. To go to 14 degrees, cooling along the saturation line is needed, which also means that air is dehumidified. Water vapor is condensed to water and must be drained away. This is also called desiccant cooling. The final point, point 2, is at 14 degrees on the saturation line. At that point, the relative humidity is 100%, the absolute humidity is 10.5 gram per kilogram, and the enthalpy is 40 kilojoule per kilogram dry air. The needed cooling is the difference in enthalpies, which is 68 minus 40 is 28 kilojoule per kilogram dry air. Let's go back to the cooling of warm air. What if we now also want to control the humidity and make sure the air at 22 degrees has a relative humidity of 50%? We start again from point 1 at 30 degrees, 35% relative humidity, and absolute humidity 12.5 gram per kilogram dry air. Point 2, 22 degrees and 50% relative humidity is here, with absolute humidity 8.5 gram per kilogram. So, to go from 1 to 2, we need to cool and to remove water vapor from the air. The quantity of water vapor that must be removed is 12.5 minus 8.5 equals 4 gram water vapor per kilogram dry air. But how does the process look like? Can you go in straight line from 1 to 2? Well, for sure not. It will represent nothing real. The air must first be cooled down from 35 to 17.5, the dew point temperature. We have learned that it goes like that, and will cost 50 minus 68 is minus 18 kilojoule kilogram energy. A minus always indicates a cooling situation, and we will just say that Q cooling, Q1C, is 18 kilojoule per kilogram. We need to remove 4 grams of water vapor to arrive to an absolute humidity of 8.5 grams per kilogram, meaning that further cooling up to the dew point on the saturation line with absolute humidity 8.5 is reached. This process needs 32 minus 50 is minus 18, which is 18 kilojoule per kilogram cooling. Unfortunately, this dehumidification has led to a huge temperature decrease to 11 degrees Celsius, which means that we must now heat the air up from 11 to 22 like that. This costs heating energy. 40 minus 32 is 12 kilojoule per kilogram. So, in total, we need to cool 18 plus 18 is 36 kilojoule, and we need to heat 12 kilojoule per kilogram. If we now look at the enthalpy difference between point 1 and 2, it is 44 minus 68 equals minus 24, meaning 24 kilojoule cooling, which is much less than what we need and do not account for the heating. This is because the enthalpy difference expresses the net heat, minus 36 plus 12. In other words, the enthalpy represents what would happen if an heat exchanger was placed between the flow to be heated and the flow to be cooled, and heat recovery between both would be 100%. The temperatures in the heat exchanger would be like that. You see them also in the Mollier diagram. In practice, such a heat exchanger is if placed, would have an efficiency lower than 100%, but it could save a lot of energy. There is another possibility to dehumidify air, and that is to absorb the water vapor it contains in a hygroscopic material like silica gel or activated alumina. Such a material is very porous and has the ability to bind water molecules in the pores on its surface. When the humid air flows along such a material, the water vapor is naturally extracted from the air and adheres in the form of water to the surface of the pores. This is called adsorption. During adsorption, the water vapor condenses and therefore releases its latent heat of evaporation, heating this way the airflow. This is the exact opposite process to adiabatic humidification, and takes therefore place on the lines of constant dew point temperature. There is no heat exchange with outside, and the process costs no energy. In the Mollier diagram, it looks like this. We use the same example as in previous slide. Instead of cooling to 11 degrees to dry the air, we can now stop the cooling at 15.5 degrees and then lead the air along the hygroscopic material in which the humidity will be absorbed along the dew point line. For the cooling along the saturation line, we now need only 6 kJ instead of 18, so the total amount of cooling needed is 18 plus 6 is 24 kJ per kilogram, and there is no heating needed. And you see that this time the enthalpy difference between points 1 and 2 is exactly the needed cooling. Point of attention here is that at a certain moment the hygroscopic material is completely saturated with water and cannot absorb any humidity. The only way to cope with that is to dry the silica gel by heating it in such a way that water is expelled. Therefore, this works as a continuous cycle. The heating needed to dry the silica is approximately equal to the heat of vaporization of water and depends on the temperature at which the heating is done. So in the end, heating is still needed. Nothing is for free. Sometimes two flows of humid air with different properties need to be mixed. It can happen in recirculation systems where, to save energy, indoor air is mixed together with outdoor air. We will study this briefly in another lecture. Be aware that very often it is not wise to mix clean outdoor air with polluted indoor air in view of hygiene. Think of the circulation of viruses like COVID-19, for example. Having said this, let's look at how this air mixing works. Imagine we want to mix a quantity MA in kilogram dry air of air in conditions A with a quantity MB of air at conditions B. What are the final conditions, point C, of the air? This can be found by looking at the mass and energy balances. Conservation of mass gives MC is MA plus MB. Conservation of water vapor mass gives MC times XC equals MA times XA plus MB times XB. By combining both equations, it appears that XC will be the barycenter of the line XA-XB with weights MA and MB, which means that graphical determination is very easy. Here is the line XA minus XB. The barycenter is then given by the distance from point A, MB times XB minus XA divided by MA plus MB, that you see here on a fictive example, meaning that in this fictive example, XC is located on the blue line. We do the same with the enthalpy, by which we can draw this second blue line. Point C is located at the intersection of both. Here, therefore, which, as you can observe, is located also at the barycenter of the line between A and C. If MB equals 0, point C is in point A, of course. If MA equals MB, point C is in the middle of the line. If MA equals 0, point C is point B. To summarize this lecture, we have learned about the most important processes that we can apply to air to bring it to wishful conditions. You are also able now to draw these processes in the Mollier diagram or a stoichiometry chart. These processes are heating and adiabatic humidification, heating and steam humidification, cooling above dew point temperature, cooling below dew point temperature, also called desiccant cooling and heating, adsorption dehumidification, and mixing of airflows. Thank you for your attention. Goodbye.